A payment partner has one requirement. Give us a single fixed IP address so our firewall can whitelist it. The app speaks HTTP, so the architect reaches for an application load balancer. Traffic spikes. The load balancer scales. Its IP quietly changes, and the whitelist breaks. The protocol was never the deciding factor. Welcome to Cloud Architect Path. Let's finish what that question started. By the end of this video, you'll know exactly when to reach for an application load balancer, a network load balancer, or a gateway load balancer, and why picking the wrong one either strips away your HTTP routing or forces you into it when you needed a static IP. That one distinction is where most load balancer decisions go sideways. In the VPC episodes, you built the network itself. Public and private subnets, route tables, NAT gateways for outbound traffic. Internet gateways handled the public-facing exposure. Now we put a managed front door in front of all those resources, and the type of load balancer you choose decides what capabilities you even have access to. Before we get into the decision rules, here are 5 terms you need in your head. First, the application load balancer, or ALB. It reads the actual HTTP request and routes based on path, host, or headers. The network load balancer, the NLB, drops down to raw TCP and UDP, which buys you extreme speed and a fixed IP address per availability zone. The gateway load balancer, GWLB, is a different animal entirely. It inserts security appliances like firewalls transparently into the packet flow. Cross-zone load balancing is a per-load balancer setting that decides whether traffic fans out across every zone or stays local to the node that received it. And a target group is the named collection of targets, instances, IP addresses, or Lambda functions that the load balancer forwards to when health checks. Here's how Amazon Web Services describes the job in its own documentation. A load balancer accepts incoming traffic and routes it to registered targets across one or more availability zones. But look at the second half. It monitors the health of those targets, and it routes traffic only to healthy ones. That health monitoring is the whole point. It's what turns a load balancer from a simple traffic splitter into a true high availability mechanism. There are 3 modern load balancer types, and they map neatly to layers of the network stack. The application load balancer lives at layer 7 and routes HTTP content, path, host, headers. The network load balancer works at layer 4, moving raw TCP and UDP at extreme speed with a static IP. And the gateway load balancer sits at layer 3, inserting third-party security appliances inline. There's also a 4th, older option, the classic load balancer. It's deprecated and being phased out, so when it shows up as an answer choice next to ALB or NLB, eliminate it first. Picture a busy airport. The application load balancer is the gate agent who reads your boarding pass, checks your identity, and directs you to the right gate based on where you're going. The network load balancer is the express security lane. It only glances at your ticket number, moves you through as fast as physically possible, always at the same fixed entrance, and you come out exactly as you went in. And the gateway load balancer is the X-ray scanner. Every passenger passes through invisibly before reaching any gate. 3 very different jobs, and that difference is the entire decision. Before we compare the 3 types, let's nail down the foundation they all share. A load balancer places a node in each availability zone you enable, and it spreads traffic across healthy targets in those zones. Here, the load balancer sends requests into 2 zones. In Zone A, both targets are healthy and receiving traffic. In Zone B, one target is healthy, but the other just failed its health check, so the load balancer pulls it out of rotation. Spreading targets across multiple zones is what removes the single point of failure. In fact, an application load balancer requires at least 2 zones. It's not a suggestion, it's a hard requirement. So how does the health check actually work? It runs as a loop. First, the load balancer sends periodic probes to each registered target. When a target misses enough consecutive checks to cross the unhealthy threshold, it's marked as failed. The load balancer then removes it from rotation, so no more traffic goes to it. Now here's the escalation. If every target in an entire zone goes down, the load balancer drops that zone's IP address out of DNS, so requests stop routing there entirely. And when targets start passing again, they're added back automatically. No manual intervention, no on-call page. There's one edge case worth understanding. What happens if every single target fails its health check across every zone all at once? The load balancer doesn't just black out and refuse all traffic. Instead, it fails open. It routes requests to all the targets anyway, regardless of the reported health. The logic is that a total DNS blackout from a misconfigured health check path is worse than sending traffic to targets that might actually still be serving. But don't mistake this for a safety net. It means a completely unhealthy fleet keeps receiving production requests. Now, cross-zone load balancing. Picture a restaurant with two serving windows. Window A has 2 staff. Window B has 8. On the left, cross-zone is off. Each window handles exactly half the line. So each person at the small window handles 25% of all customers, while each person at the big window handles just over 6%. The small window is drowning while the big one coasts. On the right, cross-zone is on. Now all customers are distributed across all 10 staff equally, so each one handles 10%. The windows, the availability zones, become transparent to the distribution. That's why uneven zones cause overload when cross-zone is off. Here's the detail that separates the types straight from the docs. For application load balancers, cross-zone load balancing is always enabled. You can't even turn it off at the load balancer level. But for network load balancers and gateway load balancers, it's disabled by default. A handy memory aid, application equals always on. That asymmetry matters because if you deploy an NLB across uneven zones and forget to enable cross-zone, one zone can quietly overload even when your total fleet has plenty of capacity. Let's lock in the shared foundation before we split the 3 types apart. All of them spread traffic across healthy targets in multiple zones. All of them use health checks to add and remove targets automatically. That's the high availability mechanism. And cross-zone is always on for the ALB, but off by default for the NLB and GWLB. With that common ground set, the real question becomes what each type can actually see and do with your traffic. That's where they diverge sharply. Let's start with the application load balancer. It functions at the application layer, the 7th layer of the network model, which means it can actually read the HTTP request. It sees the URL path, the host header, the query string, all of it. And after it receives a request, it evaluates its listener rules in priority order to decide where that request goes. That ability to read the content of a request is the single thing that sets the ALB apart from everything else, and it unlocks a whole set of features no other type has. Here's what content routing buys you in practice. A single application load balancer with one DNS name sits in front of 3 microservices. A request comes in, and the ALB reads its path. Anything to slash orders forwards to the order service target group. Anything to slash catalog goes to the catalog service. And slash users routes to the user service. 1 load balancer, 1 entry point, 3 backend services, cleanly separated by path. Before this existed, you'd have needed 3 separate load balancers or a dedicated reverse proxy to pull this off. One subtlety about how those rules work: the ALB evaluates them in priority order, lowest number first, and the very first rule that matches is the one that fires. It stops there. No further rules are checked. Think of it like a hotel reception script read top to bottom. If they ask for the spa, send them to the wellness wing. If they ask for the restaurant, send them to dining. Otherwise, general check-in. The first line that matches wins, so the order you assign priorities directly controls your routing behavior. Because the ALB understands HTTP, it can do things nothing else can. It routes on path, host header, HTTP headers, query strings, the request method, even source IP. You can attach the Amazon Web Services Web Application Firewall, or WAF, to it to inspect and filter malicious requests. It can offload authentication to Cognito or OpenID Connect, or OIDC, so your application code never even touches the token. The load balancer handles the login. And it targets not just instances, but also IP addresses and Lambda functions, while natively speaking gRPC remote procedure calls, HTTP2, and WebSockets. This is the flexible, feature-rich option. That authentication offloading is worth dwelling on. As the docs put it, you can configure an application load balancer to securely authenticate users as they access your applications. Remember Cognito user pools from the identity episode? The ALB can validate that token at the front door before the request ever reaches your code. Your application stops worrying about identity and focuses purely on business logic. And critically, this is an ALB-only capability. The network load balancer has no idea what an HTTP token even is. But there's one thing the application load balancer simply cannot do, and it's the source of the mistake from our opening. The ALB has no static IP address. Its IP addresses scale dynamically as traffic rises and falls, and architecturally there's no dedicated network interface to pin a fixed address to. So when a partner says whitelist our load balancer's IP in your firewall, the ALB is the wrong tool, no matter how much HTTP routing you need. Hold on to that, because it's about to become the whole reason the network load balancer exists. Now the network load balancer. As the docs state plainly, it functions at the fourth layer of the network model. That means it doesn't read HTTP content at all. It works with raw TCP and UDP connections. And what it gives up in content awareness, it makes up in raw power. The same documentation notes it can handle millions of requests per second. So anytime a scenario emphasizes extreme throughput, ultra-low latency, or non-HTTP protocols, your mind should jump straight to the NLB. Here's the mechanism behind the NLB's headline feature. According to Amazon Web Services, Elastic Load Balancing creates a network interface for each availability zone that you enable. That dedicated network interface, an ENI, is what gives the network load balancer a static IP address. And you can optionally attach an elastic IP to each one. So unlike the ALB, whose address is float, the NLB has a fixed post in each zone with a permanent address. That's precisely the fixed IP a firewall team can whitelist. Think of it as parking. The network load balancer's static IP is a reserved spot with a permanent address. When you enable a zone, Amazon Web Services bolts a dedicated network interface into that zone, like installing a fixed post in a specific space. That post's address never changes no matter how much traffic flows through. The application load balancer, by contrast, is a valet service using whatever spots happen to be free, so its address keeps changing as the lot fills and empties. That's the deep reason you can't just hand an ALB a static IP. It has no dedicated post to bind one to. So what actually drives you to pick a network load balancer? 4 triggers. First, non-HTTP protocols, raw TCP, UDP, or TLS pass-through, which the ALB can't handle at all. Second, a static or elastic IP per zone for firewall whitelisting. Third, ultra-low latency at millions of requests per second. with no pre-warming needed for sudden spikes. And fourth, native source IP preservation, for instance, targets, meaning your backend sees the real client IP without you parsing any headers. Any one of those, and the NLB is your answer. There's one more NLB capability that's absolutely non-negotiable. When you want to expose a service privately to other VPCs using PrivateLink, the docs are explicit. As the service provider, you create a network load balancer in your VPC as the service front end. Not an option among several, the only one. The network load balancer is the sole load balancer type that can back a VPC endpoint service. So the moment a scenario mentions a PrivateLink provider or a VPC endpoint service, the load balancer is already decided. Think back to the PrivateLink episode, where an interface endpoint put a private network interface in your subnet to reach a service. On the provider side of that connection, the service fronts a network load balancer. That's the standard PrivateLink pattern. The gateway load balancer has its own distinct endpoint type called a gateway load balancer endpoint, used for inline traffic inspection, not standard PrivateLink. The application load balancer cannot back either type of VPC endpoint service. So when you see a PrivateLink provider scenario and need to choose a load balancer, NLB is the answer for interface endpoints. One cost detail that catches people. We said cross-zone is off by default on the NLB. You can turn it on to fix uneven zone overload. Sometimes you should. But here's the catch the application load balancer doesn't have. Enabling cross-zone on a network load balancer bills you for inter-zone data transfer, since traffic now crosses zone boundaries. On the ALB, cross-zone is free. So at high volume, especially for a busy PrivateLink service, weigh that transfer cost before flipping the switch. Let's put the two side by side. The application load balancer at layer 7 requires at least 2 availability zones. A hard minimum, not a suggestion. From there, it does HTTP content routing, integrates WAF, Cognito, and Lambda targets, keeps cross-zone always on, and has no static IP. The network load balancer at layer 4 handles TCP, UDP, and TLS at ultra-low latency, gives you a static or elastic IP per zone, is the only type that backs PrivateLink, preserves the client source IP, and has cross-zone off by default with a cost to enable. When you read a scenario, the deciding factor is almost always whether you need to read the HTTP content or whether you need that fixed IP. Here's a scenario worth walking through carefully. A payment partner requires one fixed IP whitelisted in their firewall. The architect picks the application load balancer because the app is HTTP and the ALB handles that beautifully. Reasonable call. Then traffic spikes, the load balancer scales out, and its IP address changes. The partner's firewall whitelist breaks, and the integration goes dark. The requirement was a static IP and layer 7 routing at the same time. Neither type gives you both on its own. The solution is to put a network load balancer with an elastic IP in front of the application load balancer. The NLB anchors the fixed IP, and the ALB handles the HTTP routing behind it. Here's the pattern that solves it. The client hits the network load balancer first, which carries the static elastic IP the firewall whitelists. The NLB forwards that TCP traffic to the application load balancer, which applies all the layer 7 magic, path and host routing, plus WAF. And finally, the ALB sends the request on to your application targets. You get the fixed IP from the front and the content routing from the back. The NLB registers the ALB using a special ALB target group type, which Amazon Web Services added natively back in September 2021, precisely because so many teams needed both at once. Amazon Web Services describes the purpose of this hybrid directly. You can create a target group with a single application load balancer as the target and configure your network load balancer to forward traffic to it. This combines the request-based layer 7 routing of the ALB with NLB features like PrivateLink and static IP addresses. So whenever a scenario demands a static IP and HTTP routing together, or PrivateLink plus content routing, this is the sanctioned pattern. Don't waste time trying to bolt a static IP onto an ALB directly. It isn't possible. There's actually a second way to give an application load balancer a fixed IP, and knowing when to use each matters. On the left, the NLB-in-front-of-ALB pattern. It's best for regional workloads, gives a static elastic IP per zone, lives in the same VPC and account, and WAF still attaches to the ALB. On the right, global accelerator in front of the ALB. It's best for globally distributed users, provides 2 static anycast IPs that work worldwide, fails over faster than DNS, and uses edge-optimized entry points. So regional and firewall-focused, reach for the NLB. Global user base needing worldwide stable IPs, reach for global accelerator. Now the third type, which serves a completely different purpose. Amazon Web Services describes it this way. Gateway load balancers enable you to deploy, scale, and manage virtual appliances, such as firewalls. This is a load balancer for inserting third-party security appliances, next-generation firewalls, intrusion detection and prevention systems, deep packet inspection, transparently into your traffic path. It combines a single gateway entry and exit point with load balancing across a whole fleet of those appliances, scaling them up and down with demand. It is not for routing traffic to your application. The clearest way to picture the gateway load balancer is a mandatory toll booth on a highway. Every car, every IP packet has to pass through no matter where it's headed or what it carries. The toll booth sends each car through an inspection station, one of your security appliances, and if it passes, it continues to its destination with the exact same license plate. The original source and destination addresses are preserved completely. The driver never knows a separate inspection even happened. That transparency is why it's called a bump in the wire. Here's the technical fingerprint of the gateway load balancer. As the doc states, it operates at the third layer of the network model. It listens for all IP packets across all ports. There's no port filter because it's designed to intercept everything. To hand traffic to its appliances, it uses the GENEVE protocol on UDP port 6081. It wraps the original packet inside a GENEVE header, sends it for inspection, and then wraps it afterwards. So if a question ever mentions GENEVE or port 6081, the answer is the gateway load balancer every time. Let's trace the full flow across VPCs. On the left, in your consumer VPC, the route table sends traffic to a gateway load balancer endpoint. That's the mechanism that redirects packets across the VPC boundary. From there, traffic crosses into a dedicated security VPC and reaches the gateway load balancer itself. The load balancer then hands each packet down to its firewall or intrusion detection fleet for inspection. And all of that transport happens using GENEVE Encapsulation on UDP port 6081, with the original source and destination IPs preserved end-to-end. The appliances scale independently, and route tables never change when capacity does. A couple of practical notes on the gateway load balancer. Use it only to insert third-party security appliances, never as a general-purpose application load balancer, because you'd just be adding encapsulation overhead for nothing. And here's a subtle depth point. GENEVE carries layer 3 IP packets, not standard Ethernet frames. Flow stickiness keeps each connection pinned to a single appliance using a 5, 3, or 2-tuple hash, so inspection stays consistent for the life of a flow. That's also why your appliances need to be certified partner software or run custom GENEVE handling. You can't just spin up any Linux box as a target. Now let's compress everything into a single decision. Start by asking what the requirement actually says. If it needs an inline firewall or intrusion detection appliance, that's the gateway load balancer. If it calls for a static IP, a non-HTTP protocol, ultra-low latency, or a PrivateLink provider, that's the network load balancer. And if it needs HTTP content routing, WAF authentication, or Lambda targets, that's the application load balancer. When it demands a static IP and HTTP routing together, combine them. Network load balancer in front of application load balancer. And if you ever see a classic load balancer offered, migrate away from it to a modern type. Here's the single most important idea to carry out of this video. HTTP alone does not mean application load balancer. The instinct is strong. The app speaks HTTP, so reach for the ALB. But if the requirement also demands a static IP, the ALB can't deliver, and you need the network load balancer or the network load balancer in front of the application load balancer. The static IP requirement overrides the protocol. Read all the way to the last sentence of a scenario before you commit, because that fixed IP clause is exactly where the answer flips. Let's look at a concrete example of how a load balancer prevents deployment outages. A company suffers a 47-minute outage because a deployment replaced every instance at once, with no graceful traffic shifting. Here's the fix. Put an application load balancer in front and register the instances in a target group. Now, health checks keep traffic off brand new instances until they pass several consecutive checks, so a newly broken deploy is less likely to receive production requests before health checks catch it. And the deregistration delay, connection draining, lets in-flight requests finish on instances being retired. The graceful traffic shifting patterns like weighted target groups we'll cover in the production deployment video. Together, those two mechanisms limit the blast radius of any bad deployment. Let's leave you with the keyword map that turns a scenario into an answer. Static IP, whitelist IP, or elastic IP points to the network load balancer. PrivateLink provider or VPC endpoint service, also the network load balancer. Millions of requests, ultra-low latency, or UDP, again, the network load balancer. Firewall, intrusion detection, GENEVE, or port 6081 points to the gateway load balancer. Path routing, host header, path routing, host header, WAF application load balancer. And static IP plus HTTP routing together means network load balancer in front of application load balancer, while a classic load balancer answer should be eliminated first. Now let's put all of this to the test with a quick 5-question quiz. Question 1. A payment application uses HTTP and needs path-based routing. A banking partner also requires a single fixed IP address to whitelist in their firewall. Which design meets both requirements? Option A, a single application load balancer with an elastic IP attached. Option B, a network load balancer with an elastic IP forwarding to an application load balancer target group. Option C, a gateway load balancer inspecting all traffic before the application. Or option D, a classic load balancer operating at both layers. Locking your answer before I give it away. This one is B. The application load balancer gives you the path routing, but it has no static IP. You cannot attach an elastic IP to it, which rules out option A immediately. So you place a network load balancer with the elastic IP out front and register the application load balancer as its target. That combination delivers the fixed IP and the layer 7 routing at the same time. Question 2. A SaaS company wants to expose its service to enterprise customers privately across VPC boundaries using PrivateLink with no internet path. Which load balancer must front the VPC endpoint service? Option A, the application load balancer for its routing flexibility. Option B, the gateway load balancer for transparent inspection. Option C, the network load balancer, the only supported PrivateLink front end. Or option D, either an ALB or an NLB depending on the protocol. Think about which constraint matters most here. The right call here is C. PrivateLink is a hard architectural constraint. A provider's VPC endpoint service can only be backed by a network load balancer. Neither the application load balancer nor the gateway load balancer confront it, no matter what protocol the service speaks. So option D's "it depends" is a trap. There is no "it depends" with PrivateLink. Question 3. A security team must route all inter-VPC traffic through a fleet of third-party next-generation firewalls for deep packet inspection, without changing the packet source or destination addresses. Which service accomplishes this? Option A, the gateway load balancer using GENEVE Encapsulation on port 6081. Option B, the network load balancer using flow hash routing. Option C, the application load balancer with a WAF rule group. Or option D, a NAT gateway in front of the firewalls. Got your pick? Let's see. The answer is A. The phrase third-party firewalls, deep packet inspection, and preserving the original addresses points straight at the gateway load balancer. It's the only type that inserts appliances transparently in line, and it uses GENEVE on UDP port 6081 to do it. If you ever spot GENEVE or port 6081 in a question, the gateway load balancer is your answer. Question 4. An online multiplayer game backend needs UDP traffic for real-time position updates, sub-millisecond latency, and must handle millions of connections per second. Which load balancer fits? Option A, the application load balancer for high request throughput. Option B, the gateway load balancer for scaling the game fleet. Option C, the classic load balancer for dual layer support. Or option D, the network load balancer, the only type supporting UDP at that scale. Pause here if you want more time. If you said D, well done. The application load balancer is HTTP and HTTPS only. It cannot carry UDP at all, so option A is out. The gateway load balancer is for security appliances, not direct game traffic. The network load balancer is the only type that handles UDP, runs at ultra-low latency, scales to millions of requests per second, and preserves the client source IP natively, so game servers can rate limit per player. Last one. A company needs to deploy third-party firewall appliances to inspect all traffic entering and leaving their VPC. Which elastic load balancing type is designed for this use case? Option A, application load balancer, using a dedicated listener rule to mirror traffic to the firewall targets. Option B, network load balancer, using TCP pass-through to forward packets to the firewall fleet. Option C, gateway load balancer, using GENEVE Encapsulation to send traffic through virtual appliances transparently. Or option D, a classic load balancer with a custom policy that routes to the firewall target group. Got your pick? Let's see. If you said C, well done. Gateway load balancer is the purpose-built choice for inline virtual appliance deployments, firewalls, intrusion detection systems, deep packet inspection. It uses GENEVE Encapsulation on port 6081 to pass traffic through the appliance fleet transparently, preserving the original packet context so the appliance sees the real source and destination. And that's everything on elastic load balancing, ALB versus NLB versus GWLB for the exam and most of the job. Subscribe for the rest of the Cloud Architect path so you don't lose the thread. Drop a comment on what surprised you. It genuinely shapes future videos. If there's a certification you'd like me to cover, suggest it below. And tell me how the pacing and visuals work for you. Catch you next time.